So do you guys have any questions or problems I can sort out, but while we're waiting for people to show up?
Actually, yeah, I did have a question. Homework is graded based off of accuracy, not completion, right?
What do you mean by that?
I just
I'm,
saw
I'm
some
going to
class.
talk about that a little bit, but
Okay, yeah. But like we get our homework in high school. We had some classes where homework was graded off of completion instead of accuracy. But I just assumed due to the nature of this class, it was off of accuracy. Is that, or is it like what?
Yeah, so I'll repeat myself in a few minutes. I was going to say more about WebAssign because I was getting a lot of questions. But what's going to happen is uh, for each problem in WebAssign, you get 10 attempts to do it. And if
Oh,
you get it correct within those 10 attempts, you get full credit. You get 10 attempts on each problem individually.
okay, cool.
Okay, so I guess it's completion.
Okay,
Yeah, I mean, I just want you to do the work, eventually get to the place where you can finish the problem.
cool.
Yeah, anybody else have questions?
Yeah. Excuse me. The WebAssigns they're due at 11 p.m. That's Eastern time, correct?
Yes, Eastern time. All the times I give are in Eastern time. Maybe I should specify that more directly.
Oh
Because yeah, I
no,
know.
it's just because I don't know if it I'm in Los Angeles at home. I didn't know if like when it would if it when it changed over if it stayed 11 p.m. for where I was or if it moved down to 8. So I guess that makes sense.
Yeah, it'll be 11 p.m. Eastern. If that's an issue with you, we could talk, but okay. Anybody else? Looks like we got most people here. Okay, so yeah, some announcements I wanted to make. Just a reminder that you do have a few things due today. There are things due almost every day in this class, but it is worth a significant portion of your grade just to get them done. It's like 50% if you just get everything done correctly. So things that are doing, there's this short getting started assignment where I ask you to upload just a picture of your calculator and answer some few questions to help me like remember your names and faces. And then there's a quick like tutorial in WebAssign. Should take only a few minutes. And then there was the homework that was assigned yesterday that is due tonight. So these are all due by 11 p.m. Tonight. And if you need help with anything, you can either email me or if you want to talk it through with me, I'll be available tonight from 7 to 8 p.m. And the link to that will always be the same link. You can always go to, let's see, just the Canvas homepage. These links in blue will take you there. So it'd be this, let's see, you can't see my cursor. Is there a way to, but it's the one that says Wednesday, Thursdays, Fridays, 7 to 8 p.m. with Duff. That's the link I'm talking about. That should take you, it's actually the same one we're using now. So, okay. So that's homework and stuff. Yeah, then I did want to talk a little bit about the WebAssign. So just to reiterate, in WebAssign, for each problem, you get 10 attempts. So you can press submit on each problem 10 times, and it will tell you whether the answer is correct or not. And you don't get points off for getting it wrong unless you use up all 10 attempts, in which case you only get whatever credit you've gotten so far on that problem. And so you should be like submitting each problem as you finish it so that you get to save your work. You don't lose work if you do accidentally leave your computer or close the browser or something. So submit each problem as you finish it because it should count each submission of each problem individually. And just some advice on homework. In this class, it's kind of in your best interest to start doing it the day it's assigned because, the next day new homework will be assigned. And since you really only have like 2 days to do the homework, it's best like if you can get through the majority of it the first day. And then if you have questions, you can come ask us either maybe at the beginning or end of class or in the help sessions, you can ask, the few hard problems you run into, because there usually are some that everybody gets stuck on. And I would encourage you guys, if you're interested, to form, like study groups or something if you want to work with other people in the class. Oh, and then, there was one thing I forgot to mention yesterday, which I'll show you now. One place you can post questions for homework, or if you wanted to like get a study group together or something, is if you go to discussions in Canvas. I've set up one for each, basically, homework. So for each homework, you can go in here and you can ask a question. If there's a particular problem on that you're really struggling with, I can give you a hint or something. Okay. So any questions about like logistics or homework or anything before we jump back into math? No, everybody got through everything they were hoping to yesterday? Okay, then, so today's goal is to, well, ideally, I'd like you to understand the stuff that's kind of the topics of sections 1.2, 1.3, and 1.4. But basically all this stuff is it's kind of review of basic functions. Okay, so we're going to do a little bit of that now. But I encourage you also to read the sections in the textbook or skim them if you haven't done it in a while. If you haven't ever done it much at all, you might want to read it more in depth, watch the videos, that sort of stuff. But yeah, so we're going to jump right into that. Feel free to stop me if you have a question, either in chat or verbally. So I'm going to just start by telling you, like, what are the basic functions we're going to run into in this class? And there's actually one class I'm leaving out that we'll run into later. But here are what I'm thinking of as sort of the basic types of functions we're going to run into. And those are, well, the most basic ones I would say are what I would call constant functions. So these are ones where no matter what input you plug in, no matter what x value you plug in, you always get the same constant number out. So, and here, a lot of times I use the letter C to mean a constant, which means it just stands for some particular number. I'm just not telling you what that number is. So it could in principle be anything. And what do graphs of constant functions look like? Well, let's say we had f of x equals, say, -2. Well, then in whatever x value you plug in, like if you plug in 3, the output will be -2, right? If you plug in -3, you would get also -2, right? So no matter what thing you plug in, you always get -2 out. Okay, so constant functions are horizontal lines. Right? Then sort of the next most complicated thing after constant functions are another type of lines, basically all other lines. So what I would call linear functions are just lines. And there's a few different formulas for these, right? And these are going to be especially important in this class because, calculus, at the heart, what calculus really is it's the study of how functions change. And it turns out one of the best ways to sort of analyze how functions change is to approximate them by either constant functions or by lines. Okay, so we have to be pretty familiar with lines. And so, the typical formulas you'll see for lines are, there's kind of two standard ones we'll stick to. This is the slope-intercept form. Right, where m represents the slope. And what does the b represent? What do you guys think the b represents? Anybody tell me?
Y-intercept?
Yep, good job. Okay, so that's one of them. So what does a typical line look like? Well, it looks like a line, of course. So let's pick a particular line, like y equals 3x plus 4 or something. Well, that means its y-intercept is 4. So y-intercept means where it crosses the y-axis. So when x is 0, and then it has a positive slope. So it's going up from left to right. And the other kind of standard form of a line is, people remember it in slightly different ways. The way I remember it is like this. You might have a slightly different way of remembering it. That's fine. So this is called point slope form. And the reason it's called that is because it requires a point and a slope. Okay, so there's kind of two ways you can write an equation of a line. If you know the slope and the y-intercept, you can use this first one. Or if you know a point that the line passes through and its slope, then you can use this formula. And this one's going to be the one we're commonly going to use, this second one. So make sure you've used this. So like if we were to look at this line that we already drew up here, if we take this point is the point, well, the x-coordinate is 0, and then we said this had a y-intercept of 4, right? So that's the point 0, 4. So this is really our x-naught and our y-naught. And one thing you'll notice is, like, whenever I use x-naught or y-naught, I usually mean that they're just numbers. They stand for constants. So the y-intercept, or the point slope form of way of writing this, would say y minus the y value of the point, that's 4, equals 3 times x minus the point it goes through. And if you just rearrange this, you see you end up back at the same thing, right? Or sorry, m is 3. Right. If you move the 4 over. Right, so, but the reason this is more useful is because if you had some point over here where it wasn't 0 here, that it also works, right? So that's a good one to know. So that's point slope form of a line is this one. Okay, so questions about that? Okay, so the next most complicated thing, I'm sure you all have seen this, I'm just going to write down the name, are polynomials. So what's a polynomial? A polynomial is anything that is basically powers of x that have been added together and maybe multiplied by constants, as long as the powers are whole numbers. So the way we tend to write that, there's various ways, but is you can have a constant. So maybe let's, how do I, oops, let's go back to black. So it can have as many terms as it wants. It could go on, not forever, but it has to stop at some point. And, you know, maybe the last one is we'll just give it a name, a sub n, x to the n. So what's going on here is all the a's are constants, so that means they're just some numbers. Right? And so if you add up a bunch of whole powers of x multiplied by constants, that's called a polynomial. And we see these all the time, right? Like f of x is like x cubed, or 3x squared minus 47x to the 18th plus pi or something. That's a polynomial, right? Because it has constants times x to whole powers. And this one, you can have just the constant by itself as well. Okay. Okay, so those are polynomials. Those are quite nice. They're easy to take derivatives of. We'll learn later. If we combine polynomials now, we build things that are called rationals, or rational functions at least. And these are things which are just fractions, but instead of being fractions of numbers, they're fractions of polynomials. So that's just a name we're giving to these things. So whenever you hear the word rational, it usually means there's some sort of fraction going on. So this is things like 3x minus 3 over x cubed plus 1 or something like that, right? I have a polynomial on top and on bottom. I guess the only caveat is the bottom can't be just 0. You don't want this just to be the 0 polynomial. So those are called rational functions. And there's a whole bunch other ones. And we're going to spend some time later in the course like learning how to graph polynomials and rationals, like without a calculator, just using calculus techniques. Then next we have the good old trig functions. I'm not going to go through showing you all the pictures. But the ones you should be somewhat familiar with are, there's sine of x, cosine of x, tangent of x, cotangent of x, secant of x, and cosecant of x, right? Whoops, cosecant. Right, so there's those 6 are basically the ones I kind of expect you to know. Some of these have a little bit more complicated graphs. We won't use them as often, but you should know at least the basic graphs of, I would say, these first 3. Sine, cosine, and tangent. You should know those by heart. So, let's just quickly draw some graphs. So sine is the one that starts at 0. It's the kind that's called odd, which means, I'll just briefly remind you what odd means if you haven't heard that word before. We'll probably cover it later in the course again. But it means if you do something on the right side of a graph, to the right of 0, and then you reflect it over, so like imagine folding a piece of paper in half, then you would end up with something like this, right? Well, that's not odd. What odd is if you now reflect that part again. And so what you end up with is something like this. So it's kind of you're doing 2 reflections. And so this is sine of x. Right? And it has a period of 2 pi, right? It does the same shape every 2 pi. Right? This is 0 to 2 pi, and then minus 2 pi to 0. Right? So it just does that forever, goes between minus 1 and 1. Looks like a 4. Okay, so that's sine. So what I was saying is sine of x is what's called odd, which later we'll learn means that if you plug in, so if you take any x value here, and then you take the negative version of that, so that would be over here somewhere. If I take negative of that number, these two numbers, say this one is y, then this is the negative of that. So what happens is you end up with negative of f of x. And cosine, the other one, cosine of 0 is 1, so it starts up here. Let's do it in red. And it's now symmetric, or what's called even. So it does something like this. It's hard to draw it symmetrically, but you've probably seen these before. It doesn't look quite symmetrical, but it should be. And so this is cosine of x. Okay, and this one is what's called even, because it's symmetric about the y-axis. If I fold this in half, the right half and left half will match exactly. It doesn't need the extra reflection like odd does. Okay. Okay, so that's trig functions. You should be somewhat familiar with those. Then kind of the last class of things is exponentials. And these are things that look like some number to the x power, right? So these are different than polynomials because these have the x in the exponent, right? Where this, which we would call this the base, and it's always a constant. It's always a number. So like if I had something x to the x, that's not an exponential. And it's also not a polynomial. And we're going to, I mean, this only makes sense when a is positive because of sort of, you run into issues if you put a negative number as the base and then try to raise it to like the 1/2 power or something, you get square roots of negative numbers. That same issue crops up. So we're going to only use it for positive bases. And what do the graphs of these things look like? Well, maybe I'll show you something else. So one, if you're interested in graphing things, not by hand, but if you want to actually use like an online tool, there's a couple good websites. So I think this is my favorite one. It's called GeoGebra Graphing Calculator. But let's look at a couple exponential functions here. So who wants to give me a base? What base do you guys want?
4.
4. Okay, so we'll just do 4 to the x. Should get my... Right, so you see they have this sort of shape, right? And a nice thing here is that whenever you have an exponential, if it's of the form just a number to the x power, then, well, what's a number to the 0th power? It's always just 1, right? So these things will always go through 1, and then as they go off to negative infinity, they get really close to 0, right? Because you're taking, it's like 4 to the negative power is like 1 over 4 to the power, right? Negative powers mean reciprocals. And then as they go to the right, they get really, really huge, right? This one blows up off the picture almost immediately, right? If we compare that now to something like, if we choose a different type of number, I didn't want a capital there. Oops. Say we take like a fraction, like a half. Come on. So if you take a base that's between 0 and 1, instead of growing, it decays, right? Because the more powers you take of it, the smaller it gets. Like 1/2 squared is a half times a half. It's a quarter. It's getting smaller, right? But you see it still goes through the point 0, 1, right? So these are exponential functions. Okay. Okay, so let's go back to here. So these are things that, oops. So these are things like 1/2 to the x or 4 to the x. Okay, so those you're probably familiar with. Something you might not be quite as familiar with are sort of the opposite of exponentials. And we're not going to spend any time on this right now. We're going to have whole sections devoted to this later, but I might as well mention them. We have things called logarithms. So these turn out to be the opposites of exponentials, so the things that undo exponentials. And we're going to touch on something here in a few minutes. There's this special logarithm called the natural logarithm, which this probably doesn't mean anything to you right now if you haven't seen logs before, but logarithms in general have some base, just like an exponential function has a base. A log also has a base, and you can put different numbers there, and there's this special number called e that we'll talk about a little bit later today. But what do logarithm functions look like? They typically look something like this. So they look similar to a exponential graph, but they do it on the wrong axes. They go like this. So it's sort of like you rotated the exponential function somehow. I guess, yeah, it would be exactly if you rotated it on a decaying one 90 degrees to the left, or clockwise. So this is kind of what these things look like. So they're not defined for negative numbers. You can't take natural logs of negative numbers. And if you plug in 1, you get 0. So we'll come back to these later, but just want to make you aware they exist. Okay. So those are basically all the functions we're going to run into. I just wanted to make sure you know all the names and how I talk about them. Then the other kind of the main component of all these sections that we're supposed to cover today are, once you know all these basic shapes, then there's these various transformations that tell you, like, if you do a certain operation to the equation, what happens to its graph, right? And what happens if you combine them. And so there's some videos you can watch on these. We don't have time to go through every single one. But let's just go through some examples and talk our way through at least a few of them. So what we're going to do here is we're going to sketch some graphs, because it turns out that knowing how to graph things will be fairly important for us, because we need to be able to read things off from graphs sometimes. So the first one, we're going to start somewhat easy. Just do this type of thing. Okay. And then part B, we'll start with 2. Probably do 1 or 2 more. Let's see how much time we got. Okay, so why don't you take 1 or 2 minutes and get started on these. See what you think their graph should be, and then I'll show you what I think they should look like. So take a minute or 2 and try them. Okay, so this first one, well, what I see here is, I know what the graph of x squared looks like. X squared looks like a parabola like this, right? Then this coefficient out front is negative. So whenever you multiply by something by a negative, it'll flip it upside down and also stretch it a little bit vertically because of the 3. And then the 4 here, adding 4 to something moves up all the y values by 4, right? So that means it'll be, normally a parabola would start at 0, but now it's started up at 4. Whoops. So here it's going to have its vertex up at 4, and it's going to be a downward facing parabola.
Could you repeat what you said, what the -3 does to the equation?
Yeah, so basically, if you take any function and you multiply it by a negative, it flips the graph of it upside down. Does that make sense? So x squared looks like this, right? Do you agree with that?
Yeah, I understand what you're saying. I just didn't. I thought you didn't know if you said it made the 3 makes the graph wider or smaller. That's
it kind of stretches it vertically.
Okay, got it. Thank you.
If we wanted to, we could spend the time and figure out exactly what these numbers are, which would tell us how wide it is. But I'm not too worried about that. We're just looking for general sketches here. But yeah, if you wanted to figure these out, you would just set this equation equal to 0 and solve. So there were like square roots of 4/3 or something. Yeah. So for the trig one, well, here we see, and now we'll see exactly the stretching phenomenon because of the 7, right? So multiplying, so if we saw earlier what the graph of sine looks like, right? So when we multiply it by 7, that's going to multiply all the y values by 7. So instead of going between -1 and 1, it'll go between -7 and 7. So this one will look like, I guess we're doing that one in blue. So sine still starts at 0, and it still does. So we'll see that this isn't the right graph, but I want to give you kind of a step-by-step. So we'll do something like this. It's hard to make everything the right height. But now instead of these being -1 and 1, this is up here at 7, and the minimum's down here at -7. Right, but these points over here are still 2 pi, and this is pi, -2 pi.
For these type of functions, is it always positive 2 pi and negative 2 pi on both sides of it?
Yes. Well, you have to be a little careful. If it's just sine or cosine of the variable, then it has a period of 2 pi. So yeah, it goes from 0 to 2 pi and then -2 pi to 0. And then it starts repeating after these. Like these go on forever. They do the same thing forever. They do the same thing again and again.
Okay. Keep going.
No, did you have another question?
Oh yeah, and so, oh wait, that's it. Never mind. Thank you though.
Cool. So what we just graphed here is not this entire thing. What we just graphed was 7 sine of theta, right? So now what should the +8 do to it? How should I
move it up 8?
Right. So one way of doing that would be just to move the, I don't know if I can do this, but we'll see if I can. Nope, I don't know how to do that. I can draw it though. Yeah, so it's going to shift the whole graph up by 8. And so now instead of having, right, so remember it went between what two numbers? It went between -7 and +7, right? So now if I add 8 to both of those, the bottom, instead of being -1, it'll be -1 plus 8, which is 1. And then it'll go all the way up to 7 plus 8, which is what, 15. Right. So it looks something like this now. Does that make sense to people? So it got stretched by 7 and then shifted up by 8. Is essentially the two steps we did. Okay. So any more questions on that one? So let's do one more. And I think we're going to do something else in a short bit. But what about something like this? So there's 3 operations that happen to this. So first of all, the most basic part of this function is just t cubed. So can anybody tell me one of the operations that was done to t cubed here?
Does it shift right?
Yes. So yes, when you replace a variable with t minus something, so here we had this part means we were shifted to the right by 3. So that was the operation of whenever you take a variable and you replace it with t minus some number, then you shift that whole graph to the right by 3. Or if it was a plus, you shift to the left. Okay, then we saw this other operation. This will, flip it upside down and then shift it up by 2. Right? So we first start by remembering that t cubed looks something like this, right? Then maybe, so sometimes you have to be careful about like the order of these, but between the flipping and the shifting, it doesn't actually matter. So you would do something, you might flip it upside down. So do something like this. So this would be minus t cubed. Then maybe you shift it to the right by 3. Once you, if you have the hang of it, you can do this all in one step if you want. So then what we were shifting it to the right by 3. So that would look something like where this point is now 3. So that would be minus t minus 3 cubed. It's kind of a crappy graph, but you get the, then let's go to the final one. So the final one would look like this. So you would go to the right by 3, and then you'd go up by, what did I say? 2. Because of the plus 2. That's where the graph would start. Then we draw it upside down. So it probably looks something like that. Okay. So this was just sort of to remind you that that these shifting and stretching and flipping operations all still exist, and we got a tiny bit of practice with them. Okay, so we talked about exponentials. The last thing before I have you actually do some work yourselves is I want to tell you a little bit about the number e. Let me just write that word out. Okay. So in math, there's a special number called e. And it's kind of a funny little number. So its decimal representation is like this. It's 2.718, and then it has more digits. The digits actually go on forever. They go on forever, so I'll just put dot, dot, dot. Sort of, so this is, it's an irrational number. So if you don't know what that means, what it means is is that the decimal places go on forever without repeating. So there's no pattern to them. Well, I mean, there has to be some sort of pattern, but it's not an obvious one where it would just repeat a certain number of digits. So if something has a repeating segment of digits, then it's a fraction. And if it doesn't, we usually call it irrational. So fractions are rationals. Irrationals are things that are not fractions. But that, you don't really have to care about that. That's just how we've named things. So e is just some special number. And, when people talk about exponential functions and they say the exponential function, they usually mean e to the x. It's some number to the x power, right? And like, why in the world would we like to use this number, this weird number that isn't a nice number? It looks like when you first run into it. Well, so there are some reasons we like this. So some reasons we like e. So the first reason is because of calculus. So we haven't learned this yet, but it'll turn out that using this e as the base it turns out using this particular number makes the formulas as simple as possible. So later we'll learn that if you take the derivative of e to the x, it just comes back to itself. And we'll also learn that if we take the integral of e to the x, it's again itself plus possibly a constant, right? So that's one reason we like it. And the reason these formulas sort of happen is if you draw the graph of the exponential using the e base. So the exponential, right, like we saw this earlier, exponentials with a base that's bigger than 1 should be growing. And we saw that this point here is, this y value is 1. But if you draw the line that just touches here, maybe I should use the ruler for this. So if I pick the place so that the ruler just kind of grazes it and only hits the graph once at that one spot, it's hard to, then I draw that line. This line, it has a special name called the tangent line. And here it turns out to be, and so it has slope 1. So that's kind of what makes this e number special, is it makes the rate of change of this function at the origin, or at x equals 0, be 1. And that's what makes these formulas turn out so nicely. Okay, so that's reason 1. These other 2 reasons we might talk about a little later. So this one I'm going to have to be a little bit more vague on, but if you've ever thought about or taken an accounting class or something, and you thought about like how your bank actually calculates your interest, some banks might do it monthly, some might do it daily, but some banks might actually do it continuously. And it turns out to express what compounding interest at every single moment in time really means, you get some weird formula here that involves symbols you probably don't understand yet. But it turns out that all comes out to involve this number e. And sort of the last one, I don't want to spend forever on this, is this shows up also a lot in probability. So like if you, maybe I'll just say it out loud and not write this, but if you play the lottery, like if you buy one lottery ticket, but you do it a whole bunch of times, the likelihood that you win a certain amount on average, you can calculate like the probability that you win a certain amount. It's related to some, what they call the normal distribution, which is one of these exponential functions. But it has a bunch of other garbage in it too. And it comes up various other places too. It's sort of just one convenient thing. And it turns out you can convert like things that are that use the base e into other bases as well. So I don't know. But it is a number we're going to run into a lot in this class. So I want you to know it. So basically all you have to know from this is this part. This is the main thing that you have to know, is that e is just a number. It's about 2.72. Okay. And it will be related to this idea of logarithms later. We'll end up using the natural logarithm a lot later. Okay. Okay, so questions about this so far? Okay, so for the last 25 minutes of class, I'm just going to put you into groups. And I'd like you to work on, so because you have so much due today, you have a fair amount of homework. You have 3 homework assignments due tonight. So I'm going to have you work on this worksheet that is already assigned. So let me show you how to get to that. So if you go back to Canvas, our Canvas homepage, and say you go to week 1, this is worksheet 1. I forget what exactly I called it, but it's this one here, summary sheet 1, under the thing that's due Thursday. So this one here. Does everybody see that? So I'd like you with your group to work through problems 2 through 5, or however far you get. Okay? Does that make sense? You guys have questions before I let you go get started? Okay, so problems 2 through 5. Okay. Let's see, got almost everybody. So yeah, that's going to be about it for class, guys. Just a reminder that if you want to have some help with either the worksheet or the homework, I'll be available from 7 to 8 tonight. And you can find the link on the Canvas homepage. All right, so have a great day, and I'll see you tomorrow. Unless you guys have questions, I'll stick around for a few minutes.
I have one question.
Yeah.
For the on the summary sheet, when you want us to graph, do you want us to do like specific graphs or more like kind of general graphs like we did today? Like
yeah, these don't have to be super accurate. Basically, what I want is you to have the correct shape and then like one correct point. Like for a parabola, I'd like to have the correct vertex. Like for the square root one, I'd like to have it start at the right place. And
okay,
like,
great. Thank you.
Yeah, they don't have to have like all the x-intercept and all the points correct.
Okay.
Just, yeah. Anybody else have questions?
Did you see my email yet? About I just emailed you about class tomorrow. I just want to make sure you saw it. It's not a question about
Oh, yeah, you have like a doctor's appointment or something? No, that's fine. So one thing I'm going to be doing is recording the classes and posting them online on YouTube.
yeah.
So I can send you the link to that. Eventually I'll have it posted on Canvas, but
Okay, I appreciate it.
like there's nothing that'll be required or turned in class, so it's okay if you miss, but just make sure you get caught up or watch some videos or something.
Of course. Thank you. Appreciate it.
Yep, have a good day.
You too, bye.
I also have a question about the summary sheet, which is there's 2 problem 5s and we only have to answer one of them. If I'm writing out my answers physically, should I just write out problem 5?
Yeah, because one of them's not turned in. I see. I did repeat the number 5 twice.
I wasn't sure if I should change it to 6 so you know which one I'm answering, but
the answers are different enough that I'll know anyways. Yeah. But as long as you put problem 5, it'll be fine. I wouldn't worry too much about it.
Got it. Thank you.
Yep.